Look up on a clear night, away from the glow of cities, and you'll see them. Thousands of points of light scattered across the darkness like diamonds on black velvet. Some shine steady and bright, others twinkle, their light dancing through layers of Earth's atmosphere. The ancient Greeks called them asteres planetae, wandering stars, distinguishing the planets that moved across the sky from the fixed stars that seemed frozen in eternal patterns. But those wandering stars were part of our own cosmic neighborhood, members of our solar family. The fixed stars, those distant suns, remained mysteries wrapped in light years. For most of human history, we could only wonder about those distant suns. We told ourselves stories about them. We imagined, we dreamed, and always, we asked the same question. Are we alone? It's a question that has haunted us since the first humans looked skyward and recognized their own smallness against the cosmic backdrop. Picture those ancient stargazers, sitting by fires under African skies tens of thousands of years ago, watching the Milky Way stretch overhead like a river of light. What did they think they were seeing? Did they wonder what those points of light were? Did they imagine other worlds, other places, other beings looking back? Ancient philosophers certainly debated it. The Greek philosopher Epicurus, writing in the 3rd century before the Common Era, argued that infinite worlds must exist in the infinite void of space. The atomists who followed him believed that if matter and space were infinite, then the combination and recombination of atoms must produce not just one world, but countless worlds. Medieval scholars pondered it, though often within the constraints of religious doctrine that placed Earth at the center of creation. Scientists hypothesized about it with increasing sophistication as our understanding of physics and astronomy advanced. Giordano Bruno, the Italian philosopher, went further than most in 1584 when he proposed that stars were distant suns, each potentially surrounded by their own planets, some possibly inhabited. The Catholic Church found his theological ideas heretical and burned him at the stake in 1600. Though often remembered for his cosmological views, his execution stemmed primarily from religious doctrinal disputes about the nature of Christ and the Trinity, rather than his theories about planets. Still, his fate served as a grim reminder of how dangerous it could be to challenge established views of any kind during that era. But for thousands upon thousands of years, despite speculation and philosophy and wishful thinking, we had no way to answer. We could only guess, only hope, only wonder whether somewhere out there, another place where rain might fall, where mountains might rise, where rivers carved canyons and winds sculpted clouds, another place where perhaps something lived, breathed, thought, another place where perhaps creatures looked up at their own sky and asked the same question we were asking. For most of human existence, we couldn't even prove that planets existed beyond our own solar system. We assumed they must. The mathematics suggested they should. Logic dictated they probably did. But assumption isn't knowledge. Suspicion isn't certainty. And the universe, we've learned, doesn't care about what we think should be true. But then, something remarkable happened. Something that marks our generation, our moment in time, as fundamentally different from every generation that came before. We stopped wondering. We stopped guessing. We started knowing. Today, as you listen to these words, human beings have confirmed the existence of more than 6,000 planets orbiting distant stars. 6,000 worlds that just 3 decades ago we could only imagine. 6,000 answers to questions we've been asking since we first learned to ask questions at all. This is their story. The story of how we learned to see the invisible, how we discovered worlds beyond imagining, how we're now reaching out across the vast darkness of space to answer that ancient question. Are we alone? And perhaps more importantly, it's the story of what these discoveries mean, what they tell us about the universe we inhabit, about our place within it, about the nature of worlds and the possibility of life, and the sheer staggering diversity of creation itself. Tonight, we'll journey together through the cosmos, exploring planets that orbit alien suns. We'll learn how astronomers perform what seems like magic, detecting worlds trillions of miles away that they can't even see. We'll encounter super-Earths and mini-Neptunes, hot Jupiters and water worlds, planets made of diamond and planets where it rains molten glass. We'll peer into alien atmospheres searching for the chemical signatures of life, and we'll contemplate what it means to live in a universe where planets outnumber stars, where worlds are as common as sand on a beach, where every point of light in the night sky might host its own collection of circling spheres. So settle in, get comfortable, let your mind drift outward, beyond Earth's atmosphere, beyond our solar system, into the vast ocean of space where countless worlds await discovery. The universe is so much stranger, so much more wonderful than we ever dared imagine. The long road to discovery, the search for planets beyond our solar system, is a story of patience, persistence, and the slow grinding work of science. For centuries, astronomers had good reason to believe other worlds must exist. After all, our sun is just one star among hundreds of billions in our galaxy alone. What would make it special? What would make it unique? The principle of mediocrity, scientists call it. The idea that we're probably not exceptional, that what happened here probably happened elsewhere, that the universe tends towards similarity rather than uniqueness. This principle had proven powerful before. When Copernicus proposed that Earth orbited the Sun rather than sitting at the center of the universe, he was applying the principle of mediocrity. Why should Earth be special? Why should everything revolve around us? The mathematics worked better, the model was simpler, if we admitted we were just another planet. And he was right. When astronomers realized the Sun was just another star in a vast collection called the Milky Way galaxy, they were applying the same principle. Why should our star be the only one? Why should we sit at the center of creation? We didn't. We were ordinary. And that ordinariness, that mediocrity, turned out to be a path to truth. So by the 20th century, most astronomers simply assumed planets must orbit other stars. When a cloud of gas and dust collapses to form a star, conservation of angular momentum means it spins faster as it shrinks, flattening into a rotating disk. Planets form from that disk, the leftover material orbiting the newly born star. If our sun formed this way, surely others did too. But belief isn't proof. Suspicion isn't confirmation. And planets, it turns out, are extraordinarily difficult to detect. Consider the challenge from multiple angles. First, the light problem. A planet produces no light of its own. It shines only by reflecting the light of its star. And stars are blindingly, overwhelmingly bright. The sun, our modest yellow dwarf star, produces about 400 trillion watts of power. Earth, by comparison, reflects a tiny fraction of that light. Trying to see a planet next to its star is like trying to spot a firefly hovering next to a searchlight from another city. At noon, while wearing sunglasses, even the largest planet in our solar system, Jupiter, reflects only about 1/1000th of the sun's light, and Jupiter is enormous, 11 times wider than Earth, with more than twice the mass of all other planets in our solar system combined. Earth reflects even less, about 1/10,000,000th of the sun's light, and we're trying to see these faint glimmers from distances measured not in millions of miles, but in trillions upon trillions. The nearest star to our sun, Proxima Centauri, sits about 4.2 light-years away. That's roughly 25 trillion miles, or 40 trillion kilometers. To put that in perspective, if you could drive to Proxima Centauri at highway speeds, traveling 65 miles per hour without ever stopping, it would take you about 44 million years to arrive. Even light, traveling at 186,000 miles per second. The cosmic speed limit takes more than 4 years to cross that gap. Now imagine trying to photograph a planet around that star. You're looking across 4 light years at an object smaller than Earth, darker than Earth, sitting next to a star that outshines it by a factor of billions. The angular separation between the star and even a distant planet is tiny, measured in milliarc seconds, thousands of times smaller than what the human eye can resolve, smaller than what most telescopes can distinguish. Astronomers in the mid-20th century tried. They pointed their telescopes at nearby stars and strained to see anything orbiting them. They looked and looked and looked and found nothing, which didn't mean planets weren't there. It just meant they couldn't see them. Not yet. The technology wasn't ready. The techniques hadn't been invented. The sensitivity wasn't sufficient. Peter van de Kamp, a Dutch-American astronomer, spent decades studying Barnard's star, the second closest star system to Earth after Alpha Centauri. After beginning observations in the 1,940 seconds, van de Kamp announced in 1963 that he had detected wobbles in the star's position, which he interpreted as evidence of multiple planets. He published his findings. Other astronomers got excited. Here, finally, was proof of exoplanets. Except it wasn't. Later analysis showed the wobbles were artifacts, errors introduced by adjustments to the telescope itself. The planets van de Kamp thought he had discovered didn't exist. It was an embarrassing moment for exoplanet searching, a reminder of how easy it is to see patterns in noise, to mistake instrument errors for cosmic discoveries. Science is littered with such false positives, claimed discoveries that don't hold up under scrutiny. They're part of the process, necessary failures on the path to genuine understanding. But Van de Kamp's mistake didn't mean the search was futile. It just meant it was hard, harder than anyone had realized. The universe wasn't going to give up its secrets easily. For decades, astronomers tried. They pointed their telescopes at nearby stars and strained to see anything orbiting them. They developed new techniques, built more sensitive instruments, refined their methods, and found nothing confirmed. Which didn't mean planets weren't there. It just meant they couldn't see them. The breakthrough, when it came, arrived from an unexpected direction. In 1992, astronomers Alexander Wolszczan and Dale Frail weren't looking for planets at all. They were studying a pulsar, the collapsed core of a dead star spinning so rapidly it completes hundreds of rotations per second. Pulsars emit radio waves with such regularity that astronomers sometimes call them cosmic clocks. They pulse with almost perfect precision, regular as a heartbeat, reliable as sunrise. Except this pulsar, designated PSR B1257 plus 12, wasn't quite regular. Its pulse wavered, just slightly. The timing was off by microseconds, and those tiny irregularities had a pattern, a rhythm of their own. Wolszczan and Frail realized what they were seeing. The pulsar wasn't moving in a straight line through space. It was wobbling, dancing, pulled this way and that by the gravitational tug of objects orbiting around it. Planets, 2 of them, each about 4 times the mass of Earth, circling the corpse of a dead star. It was a stunning discovery, but also a strange one. These weren't welcoming worlds. A pulsar is what's left after a massive star explodes in a supernova, one of the most violent events in the universe. Any planets that existed before the explosion would have been vaporized in the blast. These worlds must have formed afterward, coalescing from the debris of stellar death, dark worlds orbiting a stellar graveyard, bathed in deadly radiation. Fascinating to astronomers, but hardly the life-bearing planets humanity had dreamed about. The real revolution came 3 years later. In 1995, 2 Swiss astronomers, Michel Mayor and Didier Queloz, announced something that seemed almost impossible. They had found a planet orbiting 51 Pegasi, a sun-like star about 50 light-years from Earth. A star that, in many ways, resembled our own sun. The planet they found was bizarre. A giant world, roughly half the mass of Jupiter, orbiting incredibly close to its star. So close that its year lasts just over 4 days. So close that surface temperatures soar above 1,800 degrees Fahrenheit. Jupiter sits far from the Sun, taking nearly 12 Earth years to complete a single orbit. But here was a gas giant hugging its star, circling it faster than our moon circles Earth. Astronomers called it a hot Jupiter, and at first, some didn't believe it existed. There wouldn't be enough material in the inner system for a giant planet to accumulate. But the data was clear. The planet was real, and its existence meant our theories needed revision. Planets, it seemed, could migrate inward after forming in the outer reaches of their systems. The universe was more dynamic, more changeable, more surprising than our neat models suggested. For their discovery, Mayer and Kalos would eventually receive the 2019 Nobel Prize in Physics. They had opened a door. They had proven that worlds exist around other sun-like stars. And once that door was open, discoveries came flooding through. By the end of 1995, we knew of 3 exoplanets. The Kepler Space Telescope, launched in 2009. During its mission, Kepler discovered more than 2,600 planets and identified thousands more candidates awaiting confirmation. Today, as of late 2024, we've confirmed more than 6,000 exoplanets, with thousands more candidates under investigation. The rate of discovery continues to accelerate. New telescopes come online. New techniques are developed. New worlds appear in our catalogs almost daily. And the most remarkable realization of all? Planets are everywhere. Statistical analysis suggests that, on average, every star in our galaxy hosts at least one planet. In the Milky Way alone, that means at least 100 billion worlds, perhaps 200 billion, perhaps more. And beyond our galaxy, countless other galaxies, each filled with billions of stars, each of those stars likely hosting planets of their own. We asked if we were alone. The universe has answered with abundance, almost beyond comprehension. We're not alone. We're surrounded by worlds, seeing the invisible. The transit method, the story of how we detect these distant planets is, in many ways, as fascinating as the planets themselves. Because remember, we can't simply point a telescope and take a picture. The glare of the star drowns out any light the planet might reflect. So astronomers had to get creative. They had to find indirect ways to detect the undetectable, ways to see without seeing. The most successful method, the technique that has discovered more exoplanets than any other, relies on something elegantly simple: shadows. Imagine standing in front of a streetlight at night. If a bird flies between you and that light, you'll see the glow dim slightly as the bird's body blocks some of the light. The bird casts a shadow, and that shadow reveals its presence, even if you're not looking at the bird itself. Planets do the same thing. When a planet passes directly between its star and Earth, when it transits across the face of its star, it blocks a tiny fraction of the starlight. The star appears to dim, just a little, for a few hours. Then the planet moves on, and the star returns to full brightness. And if there's a planet orbiting that star, the dimming will repeat with perfect regularity, once every orbit, like clockwork. This is the transit method, and its simplicity is its genius. You don't need to see the planet. You just need to measure the star's brightness with extreme precision and watch for those telltale dips. But the dips are small, astonishingly small. When Jupiter transits our sun, as viewed from a distant star system, it would cause the sun's brightness to drop by about 1%. 1%. And Jupiter is enormous, the largest planet in our solar system, 11 times wider than Earth. If Earth transited the Sun from an alien astronomer's perspective, it would dim the Sun by just 0.0084%, less than 1/100th of 1%. Detecting that requires instruments of extraordinary sensitivity. You're looking for a change of 84 parts per million in a star's brightness. It's like trying to notice when a single grain of sand is added to a beach, and yet we can do it. Modern instruments can measure stellar brightness with such precision that these tiny fluctuations become detectable. The Kepler Space Telescope, designed specifically for this task, could measure brightness changes as small as 20 parts per million, sensitive enough to detect not just Jupiter-sized worlds, but planets as small as Earth. Kepler's mission was beautifully simple in concept, if staggeringly complex in execution. It pointed itself at a small patch of sky between the constellations Cygnus and Lyra, and then it just stared. For 4 years, Kepler watched those stars with unwavering attention, measuring their brightness every 30 minutes, looking for the characteristic dips that would signal a planet crossing in front of them. The results were spectacular. Kepler discovered more than 2,600 confirmed planets and identified thousands more candidates. It found planets of every size, from rocky worlds smaller than Earth to gas giants larger than Jupiter. It found planets orbiting close to their stars and planets orbiting far away, single planets and multiple planet systems. It revealed the sheer diversity of planetary systems, the astonishing variety of worlds that exist. One of Kepler's most remarkable discoveries was a 7-planet system orbiting a small red dwarf star called TRAPPIST-1, located about 40 light-years from Earth. 7 Earth-sized worlds, all orbiting closer to their star than Mercury orbits our Sun. 3 of them sit squarely in the habitable zone, the region where temperatures might allow liquid water to exist on the surface. It's a system that seems almost designed to fascinate us. 7 terrestrial planets packed together in a cosmic dance, their orbits resonating with each other in mathematical harmony. Today, NASA's Transiting Exoplanet Survey Satellite, or TESS, continues the work Kepler began. Unlike Kepler, which stared at one small patch of sky, TESS is surveying the entire sky, scanning sector by sector, looking at the brightest, nearest stars. It's not looking for the most planets. It's looking for the best planets to study in detail. Nearby worlds around bright stars, planets whose atmospheres we can analyze, where we can search for signs of habitability and perhaps even life. The transit method tells us more than just that a planet exists. The depth of the dimming reveals the planet's size. How much light does it block? That tells us how big it is. The period of the transits tells us the length of the planet's year. How often does it cross in front of its star? That tells us how far away it orbits. And with sensitive enough instruments, we can even learn about the planet's atmosphere. When starlight passes through the thin layer of atmosphere at the planet's edge during a transit, certain wavelengths get absorbed by gases in that atmosphere. Different molecules absorb different wavelengths. Water vapor absorbs certain wavelengths. Carbon dioxide absorbs others. Methane has its own signature. By analyzing the spectrum of starlight that has filtered through an exoplanet's atmosphere, astronomers can determine what gases are present. They can analyze the air of a world they cannot see, orbiting a star dozens or hundreds of light years away. This technique, called transit spectroscopy, represents one of our best hopes for detecting life beyond Earth, because life alters atmospheric chemistry. It produces gases and maintains them at levels that pure chemistry and geology alone wouldn't sustain. Find the right combination of gases in an exoplanet's atmosphere, and you might be finding evidence of biology. But the transit method has limitations. The biggest is geometric. A planet only transits its star if its orbit happens to be aligned edge-on from our perspective. If the planet's orbit is tilted, if we're viewing the system from above or below the plane of the orbit, we'll never see a transit. The planet could be right there, obvious, large, and we'd miss it entirely because of our viewing angle. Statistically, this means we're missing most planets. We only detect the tiny fraction whose orbits happen to line up perfectly with Earth. For every planet we find via transits, many more exist that we simply can't see this way, which is why astronomers use multiple methods, each compensating for the other's limitations. And the second most successful technique works in almost perfect complement to the transit method: the stellar wobble. Radial velocity. Stars look fixed and immutable, eternal points of light that never change position. But that's an illusion. Stars move. They orbit the center of the galaxy. They drift through space. And if they have planets, they dance. Here's something that surprises many people. Planets don't orbit stars. Not exactly. Both the planet and the star orbit their common center of mass, a point called the barycenter. For our solar system, because the sun is so much more massive than any planet, the barycenter sits close to the sun's center, but not exactly at the center. Jupiter is massive enough that the Sun-Jupiter barycenter actually sits just outside the sun's surface. What this means is that as Jupiter orbits, the sun also orbits, tracing a small circle in space. The sun wobbles. It's a tiny wobble, imperceptible without careful measurement, but it's real and measurable. And if we can measure a star's wobble, we can infer the presence of planets we cannot see. This is the radial velocity method, also called the Doppler spectroscopy method. It works by exploiting something called the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes you. When something emitting waves moves toward you, the waves get compressed, the frequency increases. Light behaves the same way. When a star moves toward Earth, even slightly, its light gets shifted toward shorter, bluer wavelengths. When it moves away, the light shifts toward longer, redder wavelengths. These shifts are tiny, but they're measurable. By carefully analyzing a star's spectrum, the characteristic patterns of light and dark lines that act like a stellar fingerprint, astronomers can detect these shifts and determine how fast the star is moving toward or away from us. Now here's the clever part. If a star has a planet orbiting it, the star will wobble. As the planet swings around one side of the orbit, its gravity pulls the star toward us slightly. The star moves in our direction, and its light shifts blue. As the planet swings around the other side, it pulls the star away from us. The star recedes, and its light shifts red. Back and forth, blue to red to blue again, with a period equal to the planet's orbital period. Measure these velocity changes carefully enough, and you can determine not only that a planet exists, but how massive it is, and how far from its star it orbits. The bigger the velocity changes, the more massive the planet or the closer it orbits. Large planets close to their stars produce big, easy-to-detect wobbles. Small planets far from their stars produce wobbles so tiny they're almost impossible to measure. The precision required is staggering. Earth causes our sun to wobble at a speed of about 10 centimeters per second. That's roughly the speed of a slow-walking turtle. Now imagine measuring that speed from trillions of miles away. Imagine detecting a turtle-pace wobble in an object you can barely see, an object that's also moving through space at thousands of kilometers per second. And yet, we can do it. The most sophisticated spectrographs, instruments like HARPS at the European Southern Observatory in Chile, or ESPRESSO at the Very Large Telescope, can detect velocity changes as small as 1 meter per second. Some can push even lower, approaching 10 centimeters per second. They're getting close to the sensitivity needed to detect Earth-mass planets in Earth-like orbits. The radial velocity method gave us our first exoplanet around a sun-like star, 51 Pegasi b. That bizarre hot Jupiter was found by measuring the wobble it induced in its parent star. And in the years since, radial velocity has discovered hundreds of planets, including many that the transit method misses. Because here's the beautiful complementarity of these two techniques. Transits work best for planets with large sizes that create deep dips in starlight. Radial velocity works best for planets with large masses that create big wobbles. Use both methods on the same planet, and you get both measurements. Divide mass by volume, and you can calculate density. And density tells you what a planet is made of. A high density means rock and metal. A low density means gas and ice, like Jupiter and Saturn. Medium densities might mean something we don't have in our solar system at all. Water worlds with oceans thousands of kilometers deep, or planets with exotic compositions we're still trying to understand. Some of the most exciting exoplanet discoveries have come from combining these methods. Take the star called Kepler 2-2, about 600 light-years away. Kepler discovered a planet orbiting in its habitable zone, a world about 2.4 times Earth's radius. But Kepler could only measure size, not mass. Follow-up observations using radial velocity provided the mass estimate. Together, these measurements suggest a planet that could be rocky with a thick atmosphere or perhaps covered in a global ocean. We don't know for certain, but we know it's there, and we know its basic properties, and we know it orbits in a zone where temperature would permit liquid water. That's the power of multi-method detection. Each technique fills in the gaps left by the others. Each provides pieces of the puzzle, and slowly, planet by planet, measurement by measurement, a picture of the exoplanet population emerges. But there's one more method worth understanding. One that cuts through the fundamental challenge in a direct way. What if, instead of detecting planets indirectly through their effects, we could simply take their picture, capturing actual light? Direct imaging. Of all the ways to find an exoplanet, direct imaging seems the most obvious. Point a telescope at a star. Take a picture. Look for points of light near the star. Those are the planets. Simple, right? Except it isn't simple at all. It's phenomenally difficult, for a reason we keep coming back to. Stars are bright, absurdly, overwhelmingly bright compared to planets. A star might outshine a planet by a factor of 1 billion in visible light. Even in infrared wavelengths, where planets glow more strongly due to their heat, the star can still be 10,000 to 1,000,000 times brighter. Imagine trying to photograph a firefly hovering next to a searchlight from a mile away while someone shakes your camera. But astronomers found ways around it. The key is something called a coronagraph, an instrument that blocks out the star's light while allowing the light from objects near it to pass through. It's like creating an artificial eclipse, putting a dark disk in the optical path to block the star itself, then looking at what remains. Even with a coronagraph, direct imaging only works for certain planets, specifically young, massive planets far from their stars. Young because these planets still glow with the heat of their formation. For the first few 100 million years of their existence, large planets radiate more energy than they receive from their star, shining with infrared light from the heat trapped inside them during their violent birth. Massive because bigger planets are brighter and easier to see. The first directly imaged exoplanet, discovered in 2004, met all these criteria. Orbiting a brown dwarf called 2M1207, about 170 light-years from Earth, this planet sits roughly 40 times farther from its star than Earth sits from the Sun. It's a young world, perhaps 10 million years old, with a mass about 5 times Jupiter's. And crucially, it orbits a very dim star, a brown dwarf that itself barely shines, all of which made the planet detectable. Since then, Astronomers have directly imaged dozens of exoplanets. One of the most striking images shows 4 giant planets orbiting the star HR 8799, located about 130 light-years away. These planets, each several times Jupiter's mass, orbit at vast distances from their star. Using images captured over several years, astronomers created a time-lapse movie showing the planets actually moving in their orbits. It's one thing to know intellectually that planets orbit stars. It's another to watch it happen. To see these points of light slowly creeping around their sun in a choreographed cosmic dance that plays out over years. The James Webb Space Telescope, launched in 2021, has added to our collection of direct images. Its first exoplanet image shows HIP 65426b, a gas giant several times more massive than Jupiter, orbiting a star about 350 light-years away. Webb captured this planet in multiple infrared wavelengths, each showing different aspects of the planet's heat emission and atmospheric properties. Direct imaging offers something the other methods can't: actual light from the planet itself. When you have photons that originated from or reflected off a planet, you can analyze them. You can take spectra. You can determine atmospheric composition directly, rather than inferring it from how the planet affects starlight during a transit. For the young giant planets we can currently image, these spectra reveal atmospheres of hydrogen and helium, with traces of water vapor, carbon monoxide, and methane. Some show evidence of clouds or hazes. We're beginning to characterize these worlds not just as points of light or statistical detections, but as actual places with weather and atmospheric chemistry and unique characteristics. The future, the dream that drives much of exoplanet imaging research, is to directly photograph an Earth-like planet, a rocky world orbiting in the habitable zone of a sun-like star, a pale blue dot around a distant sun. That goal remains just out of reach with current technology. We can't quite achieve the contrast and precision needed, but future missions are being designed specifically for this purpose. NASA's Nancy Grace Roman Space Telescope, currently targeted to launch in May 2027, will test a coronagraph in space, demonstrating the technology needed for direct imaging of smaller, closer-in planets. And in the decades beyond, concepts like the Habitable Worlds Observatory envision a telescope specifically designed to capture images of Earth-like worlds and search their light for signs of life. When that day comes, when we see our first image of another Earth circling another sun, it will represent a culmination of centuries of effort. From the first crude telescopes pointed at Jupiter's moons to instruments capable of photographing planets trillions of miles away, the arc of discovery will have brought us full circle. We'll see them, actually see them. Worlds as real and tangible as our own. But even without perfect images, even working with what we have now, the portrait of exoplanet diversity that's emerging is breathtaking. And one of the first questions we ask about any newly discovered world is whether it could, in principle, host life. Which brings us to the Goldilocks zone. The Goldilocks question. Not all places are equally suitable for life. At least, not life as we understand it. And the single most important factor in determining a planet's habitability appears to be simple: liquid water. Water is strange stuff. It's one of the few substances that expands when it freezes, meaning ice floats rather than sinking. It's an excellent solvent, capable of dissolving and transporting a huge variety of chemicals. It remains liquid over a surprisingly wide temperature range. And crucially, it enabled life to arise on Earth. Every living thing we've ever found, from bacteria in boiling hot springs to fish in Antarctic waters, requires liquid water to survive. This doesn't mean life couldn't exist without water. We can imagine exotic biochemistries based on ammonia or methane or other solvents. But water is abundant in the universe, and water-based life is the only kind we know actually exists. So when we search for habitable worlds, we start by looking for planets where liquid water could exist on the surface. That means temperature. Too hot, and water boils away into vapor. Too cold, and it freezes solid into ice. There's a range of temperatures, roughly 0 to 100 degrees Celsius, at Earth-like atmospheric pressure, where water remains liquid. And for a planet orbiting a star, temperature depends primarily on distance. This is the habitable zone, sometimes called the Goldilocks zone after the fairy tale. Not too hot, not too cold, just right. It's the region around a star where a planet could potentially maintain liquid water on its surface. For our Sun, the habitable zone stretches from about 0.95 astronomical units from the Sun out to about 1.7 astronomical units. Earth sits right in the middle at 1 AU. Venus, at 0.72 AU, orbits too close and suffers a runaway greenhouse effect that has turned it into a hellish world with surface temperatures hot enough to melt lead. Mars, at 1.5 AU, sits near the outer edge of the zone but lost most of its atmosphere long ago, leaving it frozen and desiccated. But here's the crucial point. Not all habitable zones are the same. The location and width of the habitable zone depends entirely on the star. Hotter, brighter stars pump out more energy, which pushes the habitable zone farther away. A star twice as luminous as our Sun would have its habitable zone starting at about 1.4 AU, roughly where Mars orbits in our system. Cooler, dimmer stars have tighter habitable zones. A red dwarf with just 10% the Sun's luminosity would have its habitable zone starting at around 0.1 AU. Closer than Mercury orbits our Sun. Red dwarfs, also called M dwarfs, are the most common type of star in our galaxy. They're small, cool, and incredibly long-lived. While our Sun will burn for about 10 billion years total, the smallest red dwarfs could shine for trillions of years, outlasting the current age of the universe many times over. Their longevity means life would have enormous amounts of time to arise and evolve. But red dwarfs present challenges. Their habitable zones are very close to the star, which means planets there likely become tidally locked, with one face permanently facing the star and the other in eternal darkness. The star-facing side might be too hot, the dark side too cold, with only a narrow ring around the terminator boundary offering moderate temperatures. Young red dwarfs are also prone to violent stellar flares, eruptions that blast their close-orbiting planets with deadly radiation and stellar wind. These flares could strip away atmospheres, sterilize surfaces, and make the development of life difficult, if not impossible. Though it's worth noting that life on Earth arose fairly quickly despite our own planet enduring heavy bombardment in its youth. Life, once it gets started, seems remarkably resilient. At the other end of the spectrum are K-type stars, sometimes called orange dwarfs. These stars are intermediate between Sun-like G-type stars and red dwarfs. They're cooler and dimmer than the Sun, but warmer and brighter than red dwarfs, and they might represent the best of both worlds. K-dwarfs are more stable than red dwarfs, with less violent flaring. They live longer than Sun-like stars, giving life more time to develop. Their habitable zones are wider and farther out than red dwarf habitable zones, but closer in than those of Sun-like stars, making planets easier to detect. Some astronomers call K-dwarfs the Goldilocks stars. Not too hot, not too cold, not too violent, not too short-lived. Just right for life. Of course, sitting in the habitable zone doesn't guarantee a planet is habitable. Our own moon orbits at 1 AU, right in the middle of our Sun's habitable zone, and it's lifeless. No atmosphere, no water, no protection from radiation. The habitable zone is necessary, but not sufficient. A planet also needs the right size to hold an atmosphere, the right geology to maintain a carbon cycle, the right magnetic field to shield it from stellar wind, perhaps the right moon to stabilize its axial tilt. Still, It's a starting point, and astronomers have found planets in habitable zones. The nearest exoplanet to Earth, Proxima Centauri b, orbits a red dwarf just 4.2 light-years away, at a distance that puts it squarely in the habitable zone. It's about 1.3 times Earth's mass, possibly rocky, and receives roughly the same amount of stellar energy Earth gets from the Sun. Is it habitable? We don't know. Proxima Centauri is an active red dwarf known for violent flares. The planet might have lost its atmosphere long ago, or it might be tidally locked with one hemisphere roasted and the other frozen. But it might have retained an atmosphere. It might have liquid water. It might even have life. We simply don't know yet. Other intriguing worlds sit in habitable zones around different stars. Kepler 442b, about 1,200 light-years away, is roughly 1.3 times Earth's radius and orbits a K-type star. It receives about 70% of the light Earth receives from the Sun. If it has the right atmosphere, it could maintain liquid water. Kepler 186f was the first Earth-sized planet discovered in the habitable zone of another star. About 500 light-years away, orbiting a red dwarf, this world is just 10% larger than Earth and receives about 1/3 the stellar energy we receive. The TRAPPIST-1 system, with its 7 Earth-sized worlds packed close around a cool red dwarf, has 3 planets in the habitable zone, designated TRAPPIST-1e, F, and G. These worlds are prime targets for future atmospheric studies. Statistical analysis from Kepler data suggests there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of Sun-like stars and red dwarfs in our galaxy. This is an estimate with significant uncertainty, but even conservative calculations point to billions of potential worlds. 40 billion opportunities for liquid water. 40 billion possibilities for life. That number is staggering. It means that on average, the nearest habitable zone Earth-sized planet around a Sun-like star should be roughly 12 light-years away. The nearest around any star, including red dwarfs, might be as close as 4 light-years, which is why we know about Proxima Centauri b. We found it because it's one of the nearest, but proximity doesn't mean accessibility. Even the nearest stars are so far away that with our current technology, a spacecraft would take tens of thousands of years to reach them. We can study them from here, analyze their light, search for biosignatures in their atmospheres. But visiting them, walking on their surfaces, dipping our hands in their alien oceans, remains firmly in the realm of future generations. Still, knowing they exist, knowing that worlds potentially suitable for life orbit nearby stars, transforms our understanding of our place in the cosmos. We're not a rare fluke. We're likely one example among billions. And that realization leads to perhaps the most profound question of all. What exists on those worlds? Worlds we never imagined? One of the most surprising discoveries in exoplanet science is how common certain types of planets are that don't exist in our solar system at all. In our planetary system, we have a clear division. Small, rocky planets close to the Sun, Mercury, Venus, Earth, Mars. Giant planets farther out, Jupiter, Saturn, Uranus, Neptune. There's a gap. Earth, the largest rocky planet, has a diameter of about 12,700 kilometers. Neptune, the smallest giant planet, has a diameter of about 49,500 kilometers. Nothing in between. But in other planetary systems, worlds fill that gap. In fact, they dominate. The most common type of planet discovered by the Kepler mission isn't Earth-like. It's not Jupiter-like. It's something we don't have. Planets larger than Earth but smaller than Neptune. Worlds between 1.2 and 3.5 times Earth's radius. Astronomers call them super-Earths and mini-Neptunes, though these names are somewhat misleading. A super-Earth isn't necessarily a scaled-up version of Earth with familiar continents and oceans. A mini-Neptune isn't necessarily a shrunk-down version of Neptune. The names refer primarily to size, not composition or properties, and we're still figuring out what these worlds actually are. Super-Earths, generally defined as planets between 1.2 and about 2 times Earth's radius, might be rocky worlds with thicker atmospheres than Earth. They might have stronger gravity, which could hold onto hydrogen and helium more effectively, creating atmospheres nothing like what we see on rocky planets in our solar system. A super-Earth might be a water world, covered entirely by oceans hundreds or thousands of kilometers deep, with exotic forms of ice at the bottom created by immense pressure. It might have a rocky surface with active plate tectonics, volcanism, weather systems, or it might be something else entirely. The challenge is that we can't see their surfaces. We can measure their size from transits and their mass from radial velocity observations, which gives us density. But density alone doesn't tell the full story. A planet with twice Earth's radius might have Earth's density, suggesting a rocky composition, or it might be less dense, suggesting more water or a thicker atmosphere. Without detailed atmospheric studies or some way to peer beneath the clouds, we're left guessing. Mini-Neptunes, generally ranging from 2 to 4 times Earth's radius, present similar mysteries. They're clearly not gas giants like Jupiter. They're too small, but they're larger than rocky planets typically grow. The leading hypothesis is that mini-Neptunes are planets with rocky or icy cores surrounded by thick atmospheres of hydrogen and helium, atmospheres that extend thousands of kilometers above the surface and account for a significant fraction of the planet's total mass. Imagine a world where the core is solid rock or water ice, but above it stretches an atmosphere so deep and dense that it gradually transitions from gas to liquid to supercritical fluid without any clear boundary. No surface to stand on, just an ocean of air that gets denser and hotter as you descend until eventually it's compressed into liquid consistency. Weather systems thousands of kilometers tall, clouds of exotic compounds we've barely begun to understand. One of the most studied mini-Neptunes is GJ-1214b, discovered in 2009, orbiting a red dwarf about 48 light-years away. This planet is roughly 6 times Earth size, but only about 7 times its mass, giving it a density far lower than Earth's. Something is making this world puffy. Initial observations suggested it might be a water world, a planet with a significant portion of its mass in the form of water, perhaps with oceans so deep they transition to exotic, high-pressure ice phases at the bottom. Later observations have proven frustratingly difficult to interpret, with the planet's atmosphere appearing to be wrapped in clouds or hazes that block our view of the deeper layers. The boundary between super-Earths and mini-Neptunes isn't sharp. Data from Kepler revealed something called the Fulton Gap, a deficit of planets with radii between about 1.5 and 2 times Earth's radius. Planets seem to cluster either smaller or larger than this range. Why? The leading explanation involves atmospheric retention. Planets grow by accumulating material from the disk of gas and dust around their young star. Small planets might not grow fast enough to grab significant amounts of hydrogen and helium before the disk dissipates. They remain rocky. Larger planets, those that reach critical size quickly enough, can attract thick atmospheres and balloon up into mini-Neptunes. The gap represents a threshold, a critical size where planets either stay small or grow large, with few stopping in between. But this is still debated. Another possibility is that some mini-Neptunes lose their atmospheres over time, stripped away by stellar radiation and solar wind, particularly if they orbit close to their stars. The hot mini-Neptunes might be evaporating, shrinking down into super-Earths, leaving a gap in the size distribution. What's clear is that these planets are incredibly common. More common than gas giants, more common than Earth-sized worlds, at least among the planets we've detected so far. They're the universe's standard model, the default planetary type. Why don't we have any super-Earths or mini-Neptunes? The answer might be Jupiter. Massive Jupiter, forming early in our solar system's history, might have prevented any planet in the inner system from accumulating enough mass to become a super-Earth. Jupiter's gravity stirred up the inner solar system, pumping up the eccentricities of planetesimals, causing them to collide violently rather than gently accreting. This kept the rocky planets small. In systems without a massive outer giant, or with giants that formed later or farther out, things might have proceeded differently. Planets in the inner system could have grown larger, crossing the threshold into super-Earth territory, perhaps even capturing thick atmospheres to become mini-Neptunes. This means our solar system might be unusual. Not unique, but atypical. Most planetary systems might look different from ours, with one or more super-Earths or mini-Neptunes orbiting in the inner regions. The planets we grew up learning about, the template we thought was standard, might actually be an outlier. And that raises profound questions. If super-Earths are common, and if some of them orbit in habitable zones with liquid water on their surfaces, what would life be like there? The higher gravity would likely change everything. Walking would probably be harder. The atmosphere would likely be thicker, potentially creating more dramatic weather. Mountains couldn't grow as tall before collapsing under their own weight, limited by the stronger gravitational pull. Oceans might be deeper, with more vertical variation in temperature and pressure. Or consider a mini-Neptune. Scientists have even speculated whether life could exist in the atmosphere of such a world, floating in eternal clouds, never knowing a surface, sustained by chemistry and energy from above and below. On Earth, life exists in the sky. Bacteria live in clouds. Microorganisms drift through the stratosphere. Is it so implausible that on a planet with a 10,000-kilometer deep atmosphere, life might evolve to fill that aerial niche more completely? These aren't idle speculations. Though highly speculative and unproven, they're questions we might actually be able to investigate in the coming decades as we study exoplanet atmospheres in greater detail. Speaking of which, let's talk about how we read the air of worlds we cannot see, hot Jupiters and extreme worlds. Before we move to the search for biosignatures, we need to spend time with perhaps the strangest category of exoplanets, hot Jupiters. These worlds shouldn't exist according to our original theories of planet formation, and yet they were among the first exoplanets ever discovered. Their existence forced astronomers to completely rethink how planetary systems evolve. Remember 51 Pegasi b, that first planet discovered around a sun-like star in 1995. It was a hot Jupiter, a gas giant roughly half the mass of our Jupiter, but orbiting so close to its star that its year lasts just for 2 days. 4 days. Jupiter, by comparison, takes nearly 12 Earth years to complete one orbit around our Sun. At such close proximity, 51 Pegasi b experiences temperatures exceeding 1,000 degrees Celsius, hot enough to melt many metals. The planet is likely tidally locked, with one hemisphere eternally facing the star, baked by relentless radiation, while the other faces eternal night. Between these extremes, winds probably howl at thousands of kilometers per hour, trying to redistribute heat from the day side to the night side. When Mayer and Kalos announced this discovery, many astronomers were skeptical. Gas giants can't form close to their stars. There simply isn't enough material. The inner regions of a protoplanetary disk, close to the star, are too hot for ices to condense. Jupiter and Saturn formed far from the Sun, beyond what's called the frost line, where water and other volatiles could freeze into solid ice grains. These ices, along with rock and metal, provided the raw material for the giant planet's cores. A gas giant forming close to a star would be like trying to build a snowman in a desert. The materials you need simply aren't available there. So how do hot Jupiters exist? The answer is migration. Planets don't necessarily stay where they form. Interactions with the protoplanetary disk, gravitational interactions with other planets, or tidal forces can cause planets to migrate inward or outward over time. Hot Jupiters likely formed in the outer reaches of their systems, then spiraled inward, drawn by gravitational interactions with the gas disk. This was a revolutionary realization. Planetary systems aren't static, frozen in the configuration where they formed. They're dynamic, evolving, changing over millions of years. Planets can move. They can migrate vast distances. Our solar system's current arrangement might look quite different from how it started. Since that first discovery, astronomers have found hundreds of hot Jupiters. Each one is unique. Each has its own peculiarities, but they all share that fundamental strangeness of being massive gas giants orbiting perilously close to their stars. Consider HD 189733b, located about 64 light-years from Earth. This planet is slightly larger than Jupiter and orbits its star every 2.2 days. Observations have revealed that it's blue in color, not unlike Earth when viewed from space. But the similarity ends there. HD 189733b is blue because of silicate particles in its atmosphere, tiny glass-like particles that scatter blue light. The planet's dayside reaches temperatures of around 1,200 degrees Celsius, and the temperature difference between day and night drives winds that reach 8,700 kilometers per hour, several times the speed of sound. Those winds carry the silicate particles horizontally across the planet. It's a world of such hostility that nothing we can imagine could survive there. Or take WASP 76b, a planet roughly 640 light-years away. This world orbits so close to its star that its dayside temperature exceeds 2,400 degrees Celsius. At these temperatures, iron vaporizes. On the cooler night side, around 1,400 degrees Celsius, that iron condenses back into liquid droplets. The result, according to observations, appears to be iron rain falling on the planet's night side. A precipitation of molten metal droplets cascading through the atmosphere. These extreme conditions make hot Jupiters excellent laboratories for studying atmospheric physics under conditions that don't exist anywhere in our solar system. The James Webb Space Telescope has begun observing several hot Jupiters in unprecedented detail, mapping temperature variations across their surfaces, detecting specific molecules in their atmospheres, even observing how these atmospheres change over time. One of the most intriguing questions about hot Jupiters is simply, how do they survive? Orbiting so close to their stars, they're bathed in intense radiation and stellar wind. Some hot Jupiters are slowly evaporating, losing mass to space over time. Astronomers have detected extended atmospheres around some of these planets, vast clouds of escaping hydrogen streaming away into space like cosmic tails. HD 209458b, nicknamed Osiris, was one of the first exoplanets where this atmospheric escape was detected. The planet is losing roughly 100 to 600 million kilograms of material every second. That sounds like a lot, but the planet is so massive that it would take trillions of years to evaporate completely at this rate. Still, over the lifetime of the planetary system, hot Jupiters might shrink significantly. Some might not survive at all. Particularly close-in planets, orbiting in what astronomers call the evaporation desert, might lose so much mass that they're reduced to bare cores. This could explain some of the super-Earths we see orbiting very close to their stars. Perhaps they're the remnant cores of gas giants that lost their atmospheres entirely. Hot Jupiters have also taught us about tidal forces and planetary structure. When a planet orbits this close to its star, the star's gravity pulls more strongly on the near side than the far side. This tidal force can stretch the planet, heating its interior through friction. In extreme cases, these tidal forces might be strong enough to tear a planet apart. The existence of hot Jupiters also has implications for the possibility of smaller, potentially habitable planets in the same systems. If a gas giant migrated inward, it likely disrupted the inner system, ejecting or destroying any terrestrial planets that had formed there. Some hot Jupiter systems might be lonely, with no smaller planets remaining. Others might have additional planets that formed after the migration, or planets that managed to survive in stable orbits. Interestingly, hot Jupiters appear to be relatively rare. Despite being easy to detect, their large size creates deep transit signals, and their close orbits mean they transit frequently. They appear in only about 1% of planetary systems. Most stars don't have hot Jupiters. This might mean that the migration process that creates them requires specific conditions that don't always occur, or it might mean that many hot Jupiters eventually spiral all the way into their stars and get destroyed. The study of hot Jupiters has expanded to include warm Jupiters, gas giants that orbit a bit farther from their stars, with orbital periods of tens of days rather than just a few, and even some planets that seem to be transitional between hot Jupiters and more distant gas giants. Each adds to our understanding of planetary migration, atmospheric physics, and the diversity of planetary systems. What's remarkable is that these alien, extreme worlds have become almost familiar to us. We've observed them in such detail that we can describe their weather patterns, their atmospheric composition, even their color. We've watched them transit their stars thousands of times, measured their masses and sizes, mapped their temperature variations. Worlds that shouldn't exist have become some of the best studied planets outside our solar system. And they remind us, again and again, that the universe is more creative, more diverse, more surprising than our models and theories predict. The planets are out there, in configurations we didn't anticipate, with properties we didn't expect, following rules we're still learning, reading the air. Atmospheric biosignatures. Finding a planet is one thing. Understanding what it's like is another. And the key to understanding lies in the planet's atmosphere, assuming it has one. Because the atmosphere is where the action happens. Weather, climate, chemistry, and potentially the signature of life itself. We've already touched on transit spectroscopy, the technique that allows us to analyze atmospheric composition when a planet crosses in front of its star. But it's worth diving deeper into what this actually means and what we're looking for. When a planet transits, most of the starlight simply misses the planet entirely. The planet blocks a tiny fraction, causing the overall dimming we detect. But an even smaller fraction passes through the thin atmospheric shell at the planet's edge, the narrow ring of air backlit by the star. That light travels through the atmosphere, interacting with gases there. Different molecules absorb different wavelengths of light. Water vapor strongly absorbs certain infrared wavelengths. Carbon dioxide has its own absorption bands. Methane absorbs in specific parts of the spectrum. Oxygen, ozone, nitrogen compounds. Each has a unique spectral signature. By comparing the spectrum of starlight that passes through the atmosphere to the spectrum of starlight that doesn't, we can identify which wavelengths are being absorbed. Those absorption features tell us which molecules are present. It's like reading a chemical fingerprint written in starlight. The James Webb Space Telescope has revolutionized our ability to do this. Webb's infrared instruments are sensitive enough to detect the subtle absorption features from exoplanet atmospheres. In its first couple years of operation, Webb has already detected carbon dioxide, water vapor, and signs of clouds in multiple exoplanet atmospheres. It's early days, but the data is stunning in quality. But detecting gases is only the first step. The next question is, what gases would indicate life? On Earth, life has transformed the atmosphere. Oxygen comprises 21% of our air. Without life constantly producing it through photosynthesis, that oxygen would quickly disappear, combining with rocks and reduced gases. Methane, another gas we have in small amounts, would also vanish without biological sources replenishing it. So oxygen and methane together represent a chemical disequilibrium. They shouldn't coexist in large amounts. Oxygen wants to react with methane, forming carbon dioxide and water. The fact that both gases persist in Earth's atmosphere means something is actively producing them faster than they can react away, and that something is life. This is the concept behind atmospheric biosignatures. Look for gases or combinations of gases that shouldn't be present or shouldn't coexist without some active process maintaining them. If you find such a disequilibrium on an exoplanet, particularly if you can rule out non-biological sources, you might be finding evidence of life. Oxygen is the most famous potential biosignature. On Earth, nearly all atmospheric oxygen comes from photosynthesis. Plants, algae, and cyanobacteria split water molecules, using the hydrogen and releasing the oxygen as waste. Over billions of years, this process filled our atmosphere with oxygen, but oxygen isn't a perfect biosignature. Non-biological processes can produce oxygen too. If a planet loses its water, ultraviolet light from the star can split water vapor molecules, freeing hydrogen that escapes to space and leaving oxygen behind. A planet with a dying ocean might accumulate significant atmospheric oxygen with no life involved. Or consider a planet around a red dwarf. These cool stars emit lots of ultraviolet light, which can drive photochemical reactions that produce oxygen. A lifeless world orbiting the wrong kind of star might show oxygen in its atmosphere purely from stellar radiation. This is why context matters. Finding oxygen isn't enough. We need to understand the planet's whole environment. How much water does it have? What kind of star does it orbit? Are there other gases present that would help distinguish biological from non-biological sources? Methane offers similar promise and similar challenges. On Earth, most methane comes from biology. Methanogenic bacteria, which live in oxygen-free environments like swamps and the guts of animals, produce methane as a byproduct of their metabolism. Methane also comes from decomposing organic matter and, more recently, from human activities like agriculture and fossil fuel extraction. But methane can also be produced geologically. Volcanic outgassing can release methane. Chemical reactions at hydrothermal vents can produce it. Comet impacts might deliver it. If you detect methane on an exoplanet, you need to figure out whether life or geology is the source. The key, many researchers believe, is finding multiple gases in combinations that are hard to explain abiotically. Oxygen and methane together are more compelling than either alone. Add in the absence of carbon monoxide, which both biological processes would consume, and the case strengthens. Find evidence of water vapor, confirming liquid water could exist, and you're building a stronger argument. Other gases might serve as biosignatures too. Nitrous oxide is produced biologically on Earth and is stable enough to accumulate. Dimethyl sulfide, produced by marine phytoplankton, has a distinctive spectrum. Phosphine, recently claimed to be detected on Venus, though that detection remains controversial, would be difficult to produce without biology on a rocky planet. Some researchers have even suggested looking for industrial pollutants. A sufficiently advanced technological civilization might produce gases that have no natural source. Chlorofluorocarbons, for instance, are synthetic compounds that don't exist in nature on Earth. If we detect them on an exoplanet, it would be strong evidence not just of life, but of intelligent, technological life. Temporal variations might also serve as biosignatures. On Earth, carbon dioxide levels oscillate with the seasons as plants grow and die. Could we detect similar seasonal variations on an exoplanet? The changing albedo of a planet as vegetation spreads or retreats with seasons? The daily rhythm of gases produced by photosynthesis? The challenge is that biosignatures must be detected against a background of habitability markers and planetary processes that can mimic or mask biological signals. Water vapor, carbon dioxide, nitrogen, these are expected on habitable planets with or without life. They provide necessary context, but aren't biosignatures themselves, and we must be careful about false positives. We could detect what looks like a biosignature, claim we found life, and be wrong. Such a false positive would be embarrassing scientifically and damaging to public trust. So, the bar is high. Extraordinary claims require extraordinary evidence. Before we announce we've found life, we need to rule out every plausible abiotic explanation we can think of. But we must also be alert to false negatives. Life might exist but not produce detectable biosignatures. For the first half of Earth's existence, oxygen levels were extremely low, even though photosynthetic life existed. An alien astronomer studying early Earth might have concluded it was lifeless, despite it teeming with microbial life. Some planets might have life hidden beneath clouds, or life might exist underground, on a world with a thin atmosphere, producing few gases that reach detectable levels. Life might use different chemistry than Earth life, producing different gases we haven't thought to look for. This is why exoplanet atmospheric studies need to examine as many planets as possible in as much detail as possible, looking for expected signatures and unexpected anomalies. Every atmosphere tells a story. Some stories might be about wind and weather and geology. Some might be about life, and the tools to read those stories are getting better. Webb is just the beginning. Future missions like the Habitable Worlds Observatory will be designed specifically to search for biosignatures, with instruments optimized to detect oxygen, methane, and other key gases. Ground-based, extremely large telescopes with mirrors 30 meters across will use high-resolution spectroscopy to analyze exoplanet atmospheres in unprecedented detail. Within a generation or two, we might have enough data to make informed claims about life on other worlds. Or we might survey hundreds of worlds and find nothing, suggesting life is rare even if planets are common. Either answer would be profound. Either answer would change how we see ourselves and our place in the universe. The statistics of possibility. Let's step back and consider the sheer numbers. More than 6,000 confirmed exoplanets, thousands more candidates awaiting verification, new discoveries announced weekly. The catalog grows continuously, each entry representing a world we didn't know existed just years ago. And these 6,000 represent a tiny fraction of what's out there. Remember, we can only detect planets using current methods if they're close enough, bright enough, and oriented correctly from our perspective. The vast majority of exoplanets remain undetected, invisible to our instruments, too faint or too distant or too poorly positioned for us to find them. Statistical analysis helps fill in the gaps. By understanding our detection biases, how many planets we're likely missing, astronomers can extrapolate from what we see to estimate what we can't. And the estimates are staggering. Studies based on Kepler data suggest that on average, every star in the Milky Way galaxy hosts at least one planet. But the average comes out to roughly one or more per star. Our galaxy contains between 100 and 400 billion stars, depending on how you count. Let's conservatively say 200 billion. That means 200 billion or more planets in our galaxy alone. And the Milky Way is just one galaxy among trillions in the observable universe. Narrow it down. Focus on Earth-sized planets in habitable zones around sun-like and red dwarf stars. Kepler data suggests about 1 in 5 Sun-like stars hosts an Earth-sized planet in the habitable zone. For red dwarfs, the most common stars, the rate might be even higher. Perhaps 1 in 2 or better. There are billions of Sun-like stars in our galaxy. Perhaps 40 billion. 1 in 5 means 8 billion Earth-sized habitable zone planets around Sun-like stars. Red dwarfs are even more numerous. Maybe 100 billion or more in our galaxy. If half have habitable zone, Earth-sized planets, that's another 50 billion. These are rough estimates, uncertain by factors of 2 or 3. But even cutting them in half, we're talking about tens of billions of potentially habitable worlds in our galaxy, and most are far away. The nearest exoplanet, Proxima Centauri b, lies 4.2 light-years distant. That's about 25 trillion miles, or 40 trillion kilometers. Light, the fastest thing in the universe, takes more than 4 years to traverse that distance. Spacecraft travel much slower. Voyager 1, the fastest human-made object to leave the solar system, moves at about 38,000 miles per hour relative to the Sun. At that speed, it would take about 75,000 years to reach Proxima Centauri. Even our fastest probe, the Parker Solar Probe, which reaches speeds of 430,000 miles per hour when diving close to the Sun, would take about 6,600 years. The stars are far away, unimaginably far. We can see them, study them, analyze their light, but visiting them, at least with current technology, is impossible. Most of the exoplanets we've discovered orbit stars within a few thousand light-years of Earth. That's because our detection methods work best for nearby, bright stars. Beyond that distance, stars become too faint, planets too small to detect. We're sampling a tiny bubble of space around our Sun, peering into a local neighborhood that represents a minuscule fraction of the galaxy. What about the rest of the galaxy? The stars tens of thousands of light-years away, in the spiral arms we can't yet probe? The stars in the galactic center, crowded together in the dense bulge? The stars in other galaxies entirely? They almost certainly have planets too, but we can't see them. Our current instruments aren't sensitive enough. The distances are too vast, the light too faint. We're like mapmakers who have surveyed only the streets immediately surrounding our house, while the rest of the city, the continent, the world remains unexplored. But what we have surveyed reveals a clear pattern. Planets are everywhere, common as anything. The universe makes planets as naturally and inevitably as it makes stars. This realization is recent. Just 30 years ago, we knew of exactly one planetary system, ours. We suspected others existed, but we had no proof. Now we know. Planets aren't rare treasures scattered sparsely across the cosmos. They're the default state. Planetary systems are standard equipment around stars. And if planets are common, and habitable planets are common, then the ancient question comes back with renewed force. Is life common too? We don't know yet. Life might arise readily wherever conditions permit, meaning the galaxy could be teeming with biospheres. Or life might require such a specific, unlikely set of circumstances that Earth is one of a kind, alone despite countless potentially habitable worlds. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of communicative civilizations in our galaxy. It multiplies together factors like the rate of star formation, the fraction of stars with planets, the fraction of planets in habitable zones, the fraction where life arises, the fraction where life becomes intelligent, the fraction that develops technology, and the length of time civilizations survive. We now have pretty good estimates for the first few terms. Stars form at a certain rate. Most have planets. Many planets orbit in habitable zones. but the later terms remain pure speculation. We don't know how readily life arises, or how often it evolves intelligence, or how long technological civilizations typically last. Plug optimistic numbers into the Drake equation and you get thousands or millions of civilizations in our galaxy. Plug pessimistic numbers in and you might get only one: us. The truth probably lies somewhere between, but we won't know where until we gather more data. Finding even simple life, even single-celled organisms on another world, would constrain the Drake equation enormously. It would tell us life isn't a one-time fluke, but something the universe does readily given the right conditions. And if life is common, some of it might become complex, might develop intelligence, might build civilizations. Or we might search for decades and find nothing, survey 100 habitable worlds, analyze their atmospheres, find no biosignatures, no sign of life. That would be an answer too. A sobering answer. A lonely answer, but an answer nonetheless. The philosophical weight. There's a thought experiment that philosophers sometimes pose. Imagine we discover definitive evidence of life on another planet. Microscopic fossils in a Martian meteorite. Biosignatures in the atmosphere of a nearby exoplanet. Undeniable proof that life exists elsewhere. How would humanity react? Would we celebrate? Feel less alone in the cosmos? Or would we feel diminished, less special? Our religions and philosophies challenged by the knowledge that we're not unique. And then there's the flip side. Imagine we search for a century. We study thousands of exoplanets. We send probes to Mars and Europa and Enceladus. We analyze atmospheres and search for biosignatures and listen for radio signals. And we find nothing. No life. No evidence of past life. No sign that biology exists anywhere in the universe except on Earth. How would that feel? Would we feel privileged, the only consciousness in a dead universe? Or would we feel cosmically lonely, isolated beyond comprehension, the sole spark of awareness in an otherwise empty galaxy? Both answers are profound. Both would force us to reconsider our place and our purpose. Finding life tells us the universe is capable of creating life repeatedly. Not finding life tells us we might be precious beyond measure. The discovery of exoplanets has made these questions more concrete. They're no longer abstract philosophical musings. They're questions we might actually answer. We have the tools, or we're building them. We have the planets to study. Within a generation, maybe two, we'll have searched enough worlds that we can start drawing meaningful conclusions about the prevalence of life in the universe, and the philosophical implications extend beyond just whether life exists elsewhere. The sheer number of planets forces us to grapple with the Copernican principle all over again. Copernicus displaced Earth from the center of the cosmos. We're not the center of the solar system. We orbit the sun. Darwin displaced humanity from the center of biology. We're not special creations. We're one species among millions, shaped by the same evolutionary forces as everything else. And now exoplanet science is displacing Earth from the center of planets. We're not the only world. We're one among countless trillions. Every displacement has faced resistance. People want to feel special, want their home to be unique, want the universe to care about them specifically. But the universe, as far as we can tell, doesn't care. It makes planets as effortlessly and indifferently as it makes stars. Earth is one example, unremarkable in many ways, possibly unique in others, but not central, not special in the cosmic scheme. Some find this realization depressing. The vastness of space, the multitude of worlds, can make us feel small and insignificant. If there are billions of habitable planets, what does it matter what happens on ours? If the universe is so large and we so tiny, what's the point of anything we do? But there's another way to see it. Yes, we're small. Yes, the universe is vast. But we're the ones asking the questions. We're the ones building telescopes and analyzing spectra and discovering worlds. We're the ones who looked at starlight and figured out planets. We're consciousness exploring creation, the universe coming to understand itself. Carl Sagan captured this beautifully in his reflections on the pale blue dot, that famous photograph of Earth taken by Voyager 1 from beyond Neptune. Earth appears as a tiny point of light, barely visible, suspended in a sunbeam. Sagan wrote about how that image underscores our responsibility to be kind to one another, to preserve our world, because this tiny dot is all we have. Every human who ever lived here. All our wars and achievements, our loves and losses, happened on this mote of dust. The discovery of exoplanets updates that perspective. Yes, we're still small. Yes, our planet is still a pale blue dot. But now, we know there are other dots, other worlds, other places where, perhaps, other beings might look up and see their own pale dot suspended in their sky. Does that make us more or less significant? Neither, probably. Just different. We're part of a universe that makes planets. That's what the universe does. And on at least one of those planets, matter organized itself into patterns complex enough to think, to wonder, to search for other planets. That's remarkable regardless of whether it happened once or a billion times. There's a concept in philosophy called the Great Filter. It addresses the Fermi paradox, the question of why, if planets are common and the universe is ancient, we haven't detected any signs of alien civilizations. The Great Filter is some step in the process, from non-life to technological civilization, that's extremely unlikely. Maybe it's the origin of life itself. Maybe it's the jump from single-celled to multicellular organisms. Maybe it's the development of intelligence. Maybe it's the transition from intelligent species to technological civilization. Or maybe it's something that happens after civilizations become technological, some trap that destroys most civilizations before they become interstellar. The scary version is that the Great Filter is ahead of us, that most civilizations destroy themselves through war or environmental collapse or some other catastrophe before they can spread to other worlds. The hopeful version is that the filter is behind us, that the hard steps have already been overcome and technological civilizations like ours are rare but stable. Finding life on other worlds would help us understand where the filter lies. If we find simple life easily, on Mars or Europa, that tells us the origin of life isn't the filter. It happens readily. If we find complex multicellular life, that tells us the jump to complexity isn't the filter either. But if we find lots of habitable worlds and no biosignatures, no evidence of life at all, that might suggest the origin of life is the filter, and we're extraordinarily lucky it happened here. These are the kinds of questions exoplanet science forces us to contemplate. By revealing how common planets are, how many potentially habitable worlds exist, it makes the question of life elsewhere more pressing, more answerable, and more philosophically loaded. We're living through a pivotal moment in human history. Future generations will envy us. They'll grow up knowing exoplanets exist, taking it for granted that every star has worlds. But we're the generation that discovered them. We're the ones who transitioned from wondering to knowing. We're witnesses to one of the greatest discoveries humanity has ever made. Number closing. So here we are, at the end of our journey through the worlds of distant stars. We've learned how astronomers detect the undetectable, measuring tiny dips in starlight and minute stellar wobbles to reveal planets trillions of miles away. We've encountered hot Jupiters and super-Earths, mini-Neptunes and water worlds, planets so strange they challenge our theories and expand our imaginations. We've explored the concept of habitable zones, those regions around stars where temperature permits liquid water and perhaps, just perhaps, life. We've seen how astronomers are beginning to analyze the atmospheres of these distant worlds, searching for chemical fingerprints that might reveal biology. And we've contemplated the numbers. More than 6,000 confirmed exoplanets, billions more likely existing in our galaxy alone, trillions throughout the universe, a cosmos full of worlds. As you drift towards sleep tonight, consider what this means. Every star you see is likely a sun to multiple worlds. That bright point in Orion probably has planets. That star in the Big Dipper? Planets. The faint pinpoints scattered across the Milky Way? Planets around each one. Some of those worlds are balls of gas, vast atmospheres with no solid surface, storms that dwarf Jupiter's great red spot. Some are scorched rocks orbiting inches from their stars in cosmic terms, surfaces molten from heat. Some are frozen, distant, wrapped in ices of water and methane and nitrogen. Some sit in habitable zones, temperate worlds where rain might fall and rivers run and life might stir. We don't know which stars host which kinds of planets. We've only sampled a tiny fraction, but we know the diversity is there. The variety, the strangeness, the universe is wildly creative in the worlds it makes. And somewhere among those trillions of planets, there might be another world like ours. Perhaps continents rise from oceans. Perhaps an atmosphere thick with oxygen and nitrogen wraps the surface. Perhaps life has arisen, evolved, diversified. Perhaps consciousness has emerged. Perhaps, on that world, beings look up at their night sky and wonder, as we wonder whether they're alone. Or perhaps we are alone. Perhaps Earth is singular, the only world where the improbable chain of events necessary for life actually occurred. Perhaps we're the only consciousness, the only observers, the only question askers in a universe that would otherwise be forever unexamined. Both possibilities are staggering. But regardless of whether life exists elsewhere, one thing is certain. We're no longer ignorant about planets. We know they exist. We've found thousands. We'll find thousands more. And with each discovery, we learn more about how planetary systems form, how worlds evolve, what conditions permit habitability, and how common or rare life-bearing planets might be. Number. The future. Eyes on new worlds. The tools we have today are remarkable, but they're just the beginning. The next generation of telescopes and instruments will revolutionize exoplanet science in ways that make current capabilities look primitive by comparison. The James Webb Space Telescope, launched in December 2021, has already begun transforming our understanding of exoplanet atmospheres. Webb's infrared eyes can detect molecules that are invisible or barely visible to other telescopes. It can observe planets around cool red dwarf stars, where the infrared emissions are strongest. And it can build up detailed spectra over multiple transits, revealing atmospheric composition with unprecedented precision. In its first years of operation, Webb has detected carbon dioxide in the atmosphere of a gas giant called WASP-39b, found evidence of clouds and hazes on multiple planets, and even detected water vapor in the atmosphere of K218b, a mini-Neptune orbiting in its star's habitable zone. Each observation pushes the boundaries of what's possible, revealing details that were pure speculation just a decade ago. But Webb has limitations. Its primary mission isn't exoplanets, so observing time is limited. It's optimized for infrared wavelengths, which means some important biosignature gases are difficult or impossible for it to detect. And it's designed to observe planets during transits, which limits it to certain types of systems. The Nancy Grace Roman Space Telescope, currently targeted for launch in May 2027, will complement Webb's capabilities in important ways. Roman's wide field of view will allow it to survey large areas of sky, discovering planets that Webb might then observe in detail. More importantly, Roman will carry a coronagraph designed to block out starlight and directly image exoplanets. This won't be the first coronagraph in space. Hubble has one, and several other missions have tested the technology. But Roman's coronagraph represents a significant advance, designed to achieve the contrast ratios necessary for imaging planets much smaller and closer to their stars than previous instruments could handle. It's a technology demonstration, a proof of concept for the even more ambitious missions that might follow. If successful, Roman's coronagraph could directly image several dozen gas giant planets, characterize their atmospheres, and prove that the technology works well enough to scale up for detecting smaller, Earth-like worlds. It's a stepping stone, but a crucial one. On the ground, a new generation of extremely large telescopes is under construction. The giant Magellan telescope in Chile will have a primary mirror composed of 7 8.4-meter segments, giving it a combined diameter of 25 meters. The 30-meter telescope, planned for Hawaii or the Canary Islands, will have a segmented mirror 30 meters across. The European Extremely Large Telescope, also in Chile, will be the largest of all, with a 39-meter primary mirror composed of 798 individual segments. These massive mirrors will collect vastly more light than any current ground-based telescope, which means they can observe fainter objects in greater detail. For exoplanet science, this translates to the ability to directly image smaller planets, characterize atmospheric composition through high-resolution spectroscopy, and potentially detect biosignature gases in the atmospheres of nearby temperate worlds. Ground-based telescopes have advantages over space telescopes in some ways. They can be much larger since you don't have to launch them. They can be repaired and upgraded as technology advances. And they can observe continuously rather than being limited by orbital mechanics. But they're hampered by Earth's atmosphere, which distorts and absorbs light. Adaptive optic systems, which use deformable mirrors to correct for atmospheric distortion in real time, help address this problem. But they can't eliminate it entirely. The ultimate goal remains a large space telescope designed specifically to find and characterize Earth-like planets. The 2020 Decadal Survey in Astronomy and Astrophysics, which helps guide NASA's priorities, identified such a mission as a top priority for the 2030 seconds, or 2040 seconds. Provisionally called the Habitable Worlds Observatory, this telescope would combine a large primary mirror, perhaps 6 meters or more in diameter, with an advanced coronagraph or starshade, capable of blocking starlight at the extreme contrast ratios necessary to image Earth-like planets. A starshade is an intriguing alternative to a coronagraph. Instead of blocking starlight inside the telescope, a starshade is a separate spacecraft that flies in formation with the telescope, positioning itself between the telescope and the target star. The starshade is shaped like a giant flower, with specially designed petals that suppress diffraction. From the telescope's perspective, the starshade blocks the star's light while allowing light from the planet to pass around it. It's an elegant solution, though technically challenging, since it requires precise formation flying over vast distances. With a mission like the Habitable Worlds Observatory, equipped with either an advanced coronagraph or a starshade, astronomers could directly image Earth-like planets orbiting sun-like stars within 30 or 40 light-years. They could take spectra of these planets' atmospheres, searching for oxygen, methane, water vapor, and other potential biosignatures. They could observe how these atmospheres change with seasons, look for vegetation signatures, search for industrial pollutants that might indicate technological civilizations. Beyond traditional telescopes, other approaches are being explored. Gravitational lensing, where the gravity of a massive object like our sun bends and focuses light from background objects, could theoretically be used to create a kind of natural telescope. By positioning a spacecraft at the right distance from the sun, several hundred astronomical units, far beyond Pluto, astronomers might be able to use the sun's gravity to magnify and image distant exoplanets with incredible resolution. This is highly speculative and would require technology we don't yet have, but the physics is sound. Radio astronomy might also play a role. While optical and infrared observations focus on reflected starlight and thermal emission, radio observations could potentially detect artificial radio signals from technological civilizations or natural radio emissions from planetary magnetic fields. The search for extraterrestrial intelligence, or SETI, has been listening for artificial radio signals for decades. As our radio telescopes become more sensitive and our search strategies more sophisticated, we expand the volume of space we've searched and the types of signals we might detect. In the nearer term, within the next decade or two, improvements in existing techniques will continue to expand the catalog of known exoplanets. Transit surveys like TESS are discovering planets around the brightest, nearest stars, creating a target list for detailed atmospheric studies. Radial velocity spectrographs are achieving the precision necessary to detect Earth-mass planets in Earth-like orbits. Astrometry missions like the European Space Agency's Gaia are detecting planets through the tiny wobbles they induce in their stars' positions on the sky. Each technique, each new instrument, each mission adds pieces to the puzzle. We're building a comprehensive picture of the exoplanet population, understanding what types of planets are common and rare, what types of stars host what types of planets, how planetary systems form and evolve, and crucially, where we should focus our search for life. The timeline for detecting biosignatures, if they exist, is uncertain. It depends on technology development, mission funding, and luck whether the nearest potentially habitable planets happen to be oriented correctly for us to observe them in detail. Optimistic estimates suggest we might detect convincing biosignatures within 10 to 20 years. More conservative estimates push that to several decades. But the search is accelerating. The tools are improving. The target list is growing, and the questions are clearer than they've ever been. Where should we look? What should we look for? How can we distinguish true biosignatures from false positives? The framework is in place. Now it's a matter of execution, of building the telescopes, conducting the observations, analyzing the data, and whether we find biosignatures in the next decade or the next century, whether life proves common or rare, the search itself is transforming how we understand planets, how we understand habitability, how we understand our place in the cosmos. Every exoplanet we study teaches us something new. Every atmosphere we analyze expands our knowledge of planetary processes. Every discovery of a planet in a habitable zone refines our understanding of where life might arise. We're living in the golden age of exoplanet discovery. Future historians will mark this era as when humanity first looked outward and found worlds, when we transitioned from wondering to knowing, when the ancient question of whether we're alone became not a philosophical puzzle, but a scientific investigation with real data, real observations, real answers within reach. The universe is revealing its secrets. Slowly, methodically, one planet at a time, and we're here to witness it. The universe has revealed itself to be far more populated than we knew. Not with life necessarily, not yet, but with worlds. Planets fill the galaxy. And that changes everything. It changes how we see ourselves, how we understand our place. It doesn't answer the ancient question of whether we're alone, but it makes the question answerable. And the fact that we're asking, that we're searching, that we've found thousands of worlds in just 3 decades tells us something profound about human curiosity and determination. We want to know. We need to know. And slowly, carefully, with patience and precision, we're finding out. As sleep overtakes you, let your imagination drift outward, past the moon, past Mars, past the outer planets and the edge of our solar system, out into the vast darkness between stars, and know that in that darkness, worlds spin, planets orbit, Perhaps skies glow with unfamiliar colors. Perhaps waves lap at alien shores. Perhaps, somewhere, something looks upward and wonders. We are searchers. We are finders. We are the ones who looked at distant stars and refused to accept that we'd never know what orbited them. And now we know. Now we've seen them. These worlds beyond worlds, these planets around distant suns. The universe is full of them. And tonight, as you sleep, they're all out there, turning in their orbits, lit by their alien stars, waiting for the day when we finally understand them fully. If you've enjoyed this journey through the cosmos, consider subscribing to Cosmovelle. We explore the universe together, seeking knowledge and wonder in equal measure. Share this with someone who looks up at the stars and asks questions. And remember that every time you see a star, you're seeing a sun. And around that sun, very likely, worlds circle. Sleep well, dream of distant planets, and know that the search continues, every day bringing us closer to understanding our place among countless worlds in a cosmos far stranger and more wonderful than we ever imagined. Good night.